In this problem, we have two charged particles that are each producing electric fields. So here we've got particle 1 and we've got particle 2. And here we're going to be looking at location A, shown here, and we're going to be figuring out the magnitude and direction of the electric field at point A due to particle 1. The same thing, the electric field due to particle 2 at point A. And then lastly, we're going to be finding the net electric field at location A by looking at the two fields and adding them or subtracting them together based on whether they're in the same direction or whether they're in opposite directions. So to do that, we're going to be using this equation here, the electric field equation. I'm not going to go through every single step of solving this since you should be able to do that by now. So I'll just go through the outline. So first we need to find the electric field at point A due to particle 1. So for that, we're going to be putting in our charge of particle 1 for our Q. We're going to be putting in our distance between particle 1 and location A for our R. And then K is going to be our constant, which is the same every time. It's 9 times 10 to the power of 9. That gets us an electric field strength of 16,249 newtons per coulomb from particle 1. Since particle 1 is negatively charged and electric field lines go from positive towards negative, our electric field is going to be going to the left due to particle 1. Awesome. So now we're going to do exactly the same thing, but with our other particle. So now we have particle 2. So we're going to be putting into our equation our charge, our distance, and K, our constant, which is 9 times 10 to the power of 9, and calculating that out to get our electric field strength due to particle 2, which it will be 112,604 newtons per coulomb. This time, since again our particle is negatively charged, we know electric field lines point from positive towards negative. So our field lines are going to be pointing towards the particle. So our electric field direction there will be right. Now we need to figure out our net electric field at location A. Now we need to figure out our net electric field at location A. So to do that, we're going to look at the electric field from particle 1. I'm just going to draw on an arrow to show that was to the left, and it was 16,249 newtons per coulomb to the left. And we also had an electric field strength due to particle 2, which is going to the right, and it's quite a bit bigger. It's 112,604 newtons per coulomb. So since these electric fields are pointing in opposite directions, they're going to cancel each other out, and we're going to need to subtract them to get our net electric field. So I'm going to do that here. We'll have 112,604. That's our bigger number, and subtract our smaller number, which is 16,249, which gets us our net electric field strength of 96,355 newtons per coulomb. So we can fill that in over here. And the direction will be the direction of the bigger value, which was the one pointing towards the right. So our overall direction is to the right here. If our electric fields had been pointing in the same direction instead, then we would have added those values to get our net electric field. In this problem, we again have two charged particles, each producing their own electric field. This time they're arranged in a kind of triangle shape with the point that we're looking at. And again, we're going to be figuring out the electric field from each of those particles at location A. And then we're going to be finding the net electric field at that location. So same as the previous question, you're just going to use the information provided to find the electric field due to each particle. So for particle 1, we will put in the charge into our equation, the distance into our equation, and k, which is the constant, 9 times 10 to the power of 9. And that is going to give us a value for the electric field at location A of 15,849 newtons per coulomb. The direction there, since the particle is negatively charged, we know that field lines go from positive towards negative, so it's going to be going left towards that negatively charged particle. Then we'll do the same for particle 2. So for particle 2, we'll put in the charge value, we'll put in the distance, and again, the constant, which is 9 times 10 to the power of 9. Put that into our equation to get our value for the electric field due to particle 2, which is going to give us 4,068 newtons per coulomb. And the direction here, since again, the particle 2 is negative, electric field lines go from positive towards negative. The electric field lines are going towards the negative particle downwards. So that will be down. Awesome. So we now have our fields due to the individual particles. We now need to figure out how to add those together. So I'm going to draw them onto our diagram. We have particle 1 with a big field strength pointing towards the left. So 15,849 newtons per coulomb towards the left. Then we have particle 2, which has a smaller field strength and it's pointing downwards. So it's downwards and it's 4,068 newtons per coulomb. Now, if these were pointing in a straight line, kind of parallel to one another, we would add them if they're in the same direction or subtract them if they're in opposite directions. But in this problem, they're at right angles to one another. So we're going to need to use the Pythagorean theorem and trigonometry to figure out the overall net electric field strength and to figure out the direction. For the net electric field strength, we're going to be looking to find the hypotenuse of our triangle. So let's draw this out a little bit bigger to make it more clear. So I'm going to draw them tip to tail. There's my downwards field. And then tip to tail, I'm going to draw on my leftwards field, which was 15,849 newtons per coulomb. So our net field is going to be pointing in this direction here. So that's our net field, E. So first, to figure out that value, we can use the Pythagorean theorem, which is a squared plus b squared equals c squared, where c is the hypotenuse and a and b are the other sides. So we'll square root everything to get c, the hypotenuse on its own. C is the square root of a squared plus b squared. And we can put in our numbers. A was 4068 squared plus b, which is 15,849 squared. That's going to give us a value for the hypotenuse of 16,363. And our unit is newtons per coulomb. So there we found the magnitude of the net electric field, adding those together using vector addition. That gets us 16,363 newtons per coulomb. Next, to find the angle. We need to find the angle clockwise from north. So if this is north going upwards here, we need to find the angle clockwise from north, which is this angle here. So what I'm going to do is find this angle first using trigonometry, and then I'll add it to 180 degrees to get that total angle clockwise from north. So to figure out the angle, we want the opposite side and the adjacent side. So that's going to be using tangent. So we're going to be using, from SOHCAHTOA, we're going to be using tan theta is opposite divided by adjacent. And we're getting the angle on its own. So theta is going to be the inverse tangent of the opposite over the adjacent. Inverse tangent is written as tan with a -1 of the opposite side over the adjacent side. So let's add our numbers in there now. The opposite side was 15,849. The adjacent side is 4,068. We'll put that all into our calculator. Inverse tan of this fraction, making sure you're in degrees, not radians. That's going to give us an angle of 75.6 degrees. Awesome. So I found now my angle. I found this angle in here. So finally, I just need to add it to 180 degrees to get my total angle. So that'll be 75.6 plus 180, which gets me to my final angle of 256 degrees, which we can fill in here. So you can see this question is solved exactly the same way as the other question we just did. You're just finding the electric field strength and direction for each of the particles separately. Then we need to add them together using vector addition. Here, because they're at right angles, we use the Pythagorean theorem to find the net electric field. That's the hypotenuse of the triangle. Then we can use trigonometry with SOHCAHTOA to figure out the missing angle. Just make sure that you then remember to figure out the angle clockwise from north, rather than just whatever angle you calculated. In this problem, we have two charged particles arranged as shown, just as we did in the energy problems. We have the main particle, particle 1, which is stationary, and then particle 2, which is moving away from particle 1, which we can see from the motion lines shown there in the image. Particle 2 moves away to this position over here. You can see in this question, it's not moved far enough away that the potential is 0. It's still within range of particle 1. So we've been given both locations, the initial and final location. We've also been given the mass and the initial speed of particle 2. So this is going to work exactly the same as our other conservation of energy problems. The only difference is that we're going to have two types of energy at the beginning and the end. So rather than having the beginning or the end energy as 0 for each one, we're going to have to find the beginning and end energy, and we're going to have to subtract those. So starting out, we're going to be finding the electric potential energy change as our particle moves from the initial to the final location. To do that, we're going to need to find the electric potential at both locations this time, not just one. Usually one of the locations has 0 volts as the potential. This time we have electric potential at both locations. You're going to find that electric potential by putting your numbers in from the question. So I'm not going to go through every step of that. You should be confident on that by now, but this is the equation we're using for the electric potential due to a particle at a given distance away. So for the initial location, you're going to be using the charge of particle 1. That's the uppercase Q. That's our main particle. That's our charge there. You're going to be using the distance away for the initial location as our R. And K is our constant, which is 9 times 10 to the power of 9. So you'll put those values in and calculate out your electric potential at that point, bearing in mind that the electric potential may be positive or negative, depending on the type of particle we have. Since we have a negatively charged particle, we're going to get a negative potential here. So putting all those numbers in will get us a potential of negative 1.95 volts at the initial location. To figure out the electric potential at the final location, we're going to do exactly the same thing, but with the information for the final location. So again, we have the charge of the main particle. That's going to be the same. We're still looking at the electric potential due to particle 1. K is still going to be 9 times 10 to the 9, that constant. The only difference in this equation is going to be the distance away. Now that's for our final location, which is given here. So you'll put those numbers in and you'll get out your final electric potential at the final location, which is 1.02 volts. So rather than one of these being 0, I have a value at both locations. So now to find the potential difference, rather than it just being the value, since the other one was 0, we're going to need to subtract those. So find the difference between those two values to get your potential difference. So I'll subtract those, and that will get me 0.93 volts. So I found the magnitude of the potential difference now. So I've got all I need to figure out my electric potential energy. Since I've got my potential difference, delta V, here, and I know the charge of my test particle here, so I can put those values in to find my electric potential energy. Again, I'm not going to calculate that out because you should be able to do it by now, but here that gives me an change in electric potential energy of 5.97 times 10 to the negative 19 joules. So I know my change in electric potential energy. Next, I need to find my change in kinetic energy. And we know because of the conservation of energy, my total energy remains constant. So whatever my change in electric potential energy, that's going to be made up by an equal change in kinetic energy. So our change in kinetic energy will be exactly the same. It's also going to be 5.97 times 10 to the negative 19 joules. So we now know the change in kinetic energy. However, we can't just use that to find our speed, since we have kinetic energy at the beginning and at the end. So we found our change in kinetic energy, which was 5.97 times 10 to the negative 19 joules. But in this question, we have initial kinetic energy and final, and the change between them is given by that much that we've just found. So first, let's figure out our initial kinetic energy. We can figure this out because we know the initial speed and we know the mass of the particle. So we know both m and v in our kinetic energy equation at the initial location. So we can use that to figure out our initial kinetic energy. If you put those values of m and v into your equation, you will get a value of 3.01 times 10 to the negative 18 joules for your initial kinetic energy. So we can fill that out here. And in this problem, we know our particle is being attracted back towards the main particle. So it's slowing down as it moves away. So we started with this much energy. Then we had a change of this much energy, and we know it's decreasing since it's slowing down. So to get my final kinetic energy here, I'm going to take my initial kinetic energy and I'm going to subtract the change in kinetic energy to get the final. So if you put those values for the initial kinetic energy into our equation and for the final kinetic energy as well, we can calculate out our final kinetic energy, which is 2.42 times 10 to the negative 18 joules. Now our final job is to find our final speed of particle 2. We now know the final kinetic energy of particle 2, so we know the kinetic energy. We still know the mass of particle 2, that hasn't changed. So all we need to do is put those into our equation to figure out our final speed. Again, I'm not going to do that. You should be confident on that by now, but that gives us a final speed of 4,397 meters per second. So that outline hopefully gives you a hint for how to get started on this problem. And you can see it works exactly the same way as all the other conservation of energy problems we did in this unit. The only difference is that we have electric potential energy and kinetic energy at both the beginning and the end. So instead of thinking out of one of those as being 0, we need to look at both and subtract them to get the change.